In this episode, we will talk about large language models, LLMs, for time series analysis. We've got a really interesting survey paper here called Towards Cross-Modality Modeling for Time Series Analytics, a survey in the LLM era. And our mission today is, well, it's to dig into how recent research is tackling this fundamental challenge, using LLMs, which are trained mostly on text, for time series data. It's a different beast entirely. We want to understand how they're bringing textual knowledge into play to improve things like forecasting, classification, filling in missing data, anomaly detection. So we'll cover the different kinds of text people are using, the main strategies for bridging this gap. They talk about alignment and fusion, what experiments show works best, and where the research might go next.
Exactly. And the core problem, like you said, is this cross-modality gap. LLMs are amazing with language, obviously, but they learn from text structures. Time series data, well, it's sequential. It has these statistical dependencies, temporal dynamics. It's just fundamentally different information. So this research is all about trying to harness that power of LLMs, but finding smart ways to connect their text understanding to the specifics of time series.
Right. So let's start with how researchers are even getting time series info into a format LLMs can understand. The paper lays out 4 main types of textual data. Can you walk us through those?
Sure. First up is the numerical prompt, often called PN. The basic idea here is pretty straightforward. You just directly translate the numerical sequence into text. Think of it like turning a list of numbers into, well, a sentence.
Okay.
Like if you had temperatures, 20, 22, 21 degrees. Exactly. You might write, the temperature was 20 degrees Celsius, then 22 degrees Celsius, then 21. You get the idea. The question is, can the LLM pick up on the underlying numerical patterns even when it's presented linguistically, almost like it's reading a story about numbers changing?
That is very direct. Okay, what's the second type?
The second is the statistical prompt, or PS. Now, instead of the raw numbers, this encodes statistical features derived from the time series into text. So things like the mean, the maximum, the minimum over a certain period, standard deviation, maybe even trends or seasonality information.
Ah.
So for our temperature example, a statistical prompt might be something like, the average temperature was 21.5 degrees, high of 23, low of 20, showed a slight upward trend. It gives a higher level summary, the key characteristics, without needing every single data point.
Right. Conveys the gist without the raw sequence. Makes sense. And the third type?
Third is the contextual prompt, PC. This one brings in outside auxiliary text information that's relevant to the time series. This could be quite broad metadata about the data set, maybe news articles that happened during that time.
Oh, interesting. Like events.
Yeah, exactly. Event information, maybe expert reports about the domain, social media chatter if it's relevant. For the temperatures, maybe a heat wave was reported in the region during the latter part of this period. The goal is to inject real-world context that you wouldn't get just from the numbers alone.
So you're adding descriptive context that might explain why the numbers are doing what they're doing. Okay. And the last one?
The fourth is word token embedding, just WX. This is a bit different. It's more about using the LLM's internals directly. Instead of writing a specific prompt, researchers might try using the pre-trained numerical representations, the embeddings for words or tokens from the LLM itself, as a stand-in, somehow, for the time series information. The bet here is that the LLM's training on vast text gives it a rich semantic space where even numerical patterns, if mapped correctly, might reveal useful sequential structures.
And the paper also mentions hybrid prompts, combining these.
Exactly, good point. Since each type gives a different angle, some studies mix and match. They create hybrid prompts, maybe combining PN, PS, and PC. The thinking is, if you combine the raw numbers, the stats, and the context, you give the LLM a much richer, more complete picture, potentially leading to better results.
Okay, so we have these different ways to sort of textify time series data or related info.
Yeah.
Now, the big question, how do researchers actually use this text together with the original time series for tasks like forecasting? The paper talks about cross-modality modeling. What's the main objective there?
Right. The fundamental goal of cross-modality modeling here is to learn some function. Let's call it $5. This function takes 2 inputs. The time series data itself, $6, and the related textual data, $T. And the output, dollars, is whatever you need for your task. A forecast, a classification label, imputed values, an anomaly flag. So formally, we want to learn phi-fx t, right arrow I ROI. The real challenge, and where all the different methods come in, is designing that function $5 to effectively bridge the gap between $6 and $. How do you align them? How do you fuse them meaningfully?
That sets things up perfectly. Let's dive into those strategies. First up, cross-modality alignment. What's the core idea behind alignment?
Alignment strategies are all about learning the connection, the association between the representations of the time series and the text. The goal is basically to map both these different types of data into some shared space, a latent space, where their relationships are easier to see and work with. If you align the representations, the model can then use info from one modality to, well, better process the other. The paper covers a few key ways to do this alignment.
Okay, let's start with retrieval. Sounds like pulling relevant info from one side using the other.
Exactly. Retrieval-based alignment uses one modality to selectively grab useful bits from the other. The paper breaks it down by direction. First is unidirectional retrieval. Information flow is mainly one way in a given step.
Can you give an example of how that works with time series and text?
Sure. Time CMA, that's time series forecasting via cross-modality alignment, is a good one. They use those hybrid prompts we talked about, numerical, statistical, contextual, feed them to an LLM to get prompt embeddings. Then they align these prompt embeddings with the embeddings from the original time series data. It's unidirectional because the time series embeddings act like queries to pull out the most relevant parts from the LLM's prompt embeddings to improve the forecast.
Okay, and the paper mentions others too, like time LM, tempo. How do they fit in?
Right, so time LLM, time series forecasting with large language models, time FFM, time series forecasting via LM-empowered federated foundation model, S2IP LLM, semantic space-informed prompt learning with LLM, and CALF, cross-modal alignment and fine-tuning of LLMs for time series forecasting. They often work by using the time series embeddings as queries to retrieve relevant info, maybe aligned word token embeddings, from a pre-trained LLM tempo, prompt-based generative pre-trained transformer for time series forecasting, does it the other way around. It uses embeddings from the textual prompts as queries to retrieve corresponding values directly from the time series itself, which they usually patch or segment first.
So the query can go time series to text or text to time series. How does this retrieval actually happen technically? Is there a common mechanism?
Yeah, the paper points to cross-attention mechanisms as being really common here. You can think of it like this formula. EA is the final aligned embedding. Q are the queries, say, from the time series embeddings. 2x and the dollars are the keys and values. Maybe from the LLM's textual embeddings, ET. Often there are learnable matrices, 2xq, WK, WEDV, to transform these inputs first. Cross-attention then calculates a weighted sum of the values, where the weights depend on how similar the queries are to the keys. It lets the query modality pay attention to the most relevant parts of the other modality.
Got it. That clarifies the mechanics of unidirectional retrieval. Now, what about bidirectional retrieval? How's that different and what's the advantage?
Bidirectional retrieval basically lets both sides act as queries. The time series embeddings can query the text, and the text embeddings can query the time series. This allows for a more dynamic back-and-forth exchange of information.
Like a conversation between the modalities.
Yeah, exactly. Instead of just one-way flow, they can both refine their understanding based on what's relevant in the other. Potentially leads to deeper integration and better performance across more tasks and domains.
Can you give an example of a model using this bidirectional approach?
Lorette Language-Empowered Retentive Network for Time Series Forecasting is a key example. It doesn't just use time series to query text, it lets the text embeddings also retrieve relevant features from the time series. It creates this kind of iterative refinement loop, leveraging both the temporal patterns and the semantic knowledge.
And dual time in healthcare. That sounds interesting too.
Yes, dual time is designed specifically for healthcare tasks like forecasting or classification using medical data. It integrates textual clinical reports with time series data like, say, ECG signals. This bidirectional interaction helps it understand the patient's physiological signals in the context of the doctor's notes, and vice versa. You can see how that could be really powerful in a clinical setting.
Definitely. How is this two-way street represented mathematically in these models?
The paper often describes it as a two-stage process. Stage 1 might map the textual knowledge into the time series feature space. You could use cross-attention like ET, AT, EXHO, ET, ET, ET. ET is the text embedding transformed to align with the time series space, EXHO. Then stage 2 integrates this aligned text knowledge back with the original time series features, maybe again with cross-attention, EAX, EETA. This gives you the final aligned embedding EA, incorporating info flowing both ways.
That seems more intricate, potentially more powerful. Right. Okay, the next alignment strategy you mentioned is contrastive learning. What's the idea behind this for cross-modality time series?
Contrastive learning at its core is about learning a shared space where things that should be similar are pulled together and things that shouldn't be similar are pushed apart. So for time series and text, you want the embedding of a time series and its corresponding text description to be close.
Okay.
But you want the embedding of that same time series to be far away from the embeddings of unrelated text descriptions. You maximize agreement for positive pairs, correct time series text match, and minimize it for negative pairs, incorrect matches. This forces the model to learn representations that capture the essential shared meaning.
How does that play out specifically with LLMs and time series?
Well, take LLM-TSI, LLM for Time Series Integrator. They use contrastive learning to align representations from a smaller time series model with text representations from a big LLM by maximizing mutual information for the paired data. Or METS, Medical Event Time Series, they use automatically generated clinical reports to help pre-train an ECG model. The contrastive part ensures an ECG signal is similar to its own report, but dissimilar to other patients' reports.
Makes sense.
And another one, test text prototype aligned embedding to activate LLM's ability for time series, trains an encoder using a contrasting objective that aligns the time series space with the LLM's embedding space using various contrasts, instance-wise, future-wise, and text prototype-based.
And the paper gives a general formula for this contrastive loss.
Yes, a common form looks something like this. Lane contrast, log left ex, some bexe, right? So textsim is just a similarity function, often cosine similarity. Tau is a temperature parameter that kind of controls the focus. How hard do you push apart the negatives? Liangaller is your set of negative samples, the text embeddings that don't match the time series. Minimizing this loss function effectively pulls the positive pair EATT together in the embedding space while pushing all the negative pairs away.
Okay, that covers contrastive learning. The last alignment approach is knowledge distillation, or KD. This is about teaching a smaller model from a big one, right?
Exactly. Knowledge distillation is about transferring capabilities from a large, powerful, but maybe slow or expensive teacher model, like a big LLM, to a smaller, more efficient student model. The goal is to get comparable performance from the student, but with less computational cost, making it practical for real-world deployment. And researchers are exploring KD as a way to tackle this cross-modal alignment problem for time series and text.
The paper differentiates black box and white box KD. What's the main difference there?
It boils down to how much access you have to the teacher's internal workings. Black box distillation treats the teacher like, well, a black box. You only use its inputs and outputs to train the student. CALF, which we mentioned earlier, uses this approach. In its distillation part, it tries to make the student model's intermediate layer outputs match the teacher's outputs when they process related data. It also makes sure their final predictions are consistent. The paper mentions loss functions like a fire and output for matching these intermediate and final results, guiding the student without needing to see the teacher's parameters.
And white box distillation.
White box distillation does use internal information from the teacher. Time KD is the example given. It doesn't just match the teacher's output predictions. It also tries to align the student's internal attention maps with the teacher's attention maps. This gives the student richer information, not just what the teacher predicts, but how it arrived at that prediction by attending to different parts of the input.
Okay, so alignment tries to build bridges between the modalities. The other main strategy is cross-modality fusion. How does fusion differ?
Fusion is more direct. Instead of just aligning them in a shared space, it aims to combine the text and time series data into a single, unified representation. You essentially create one feature vector that contains information from both. Now, this can be powerful because you might capture complementary information, but the paper warns it can sometimes lead to data entanglement, blurring the lines between the modalities, which might actually hurt performance compared to careful alignment.
Interesting trade-off. The paper mentions two main fusion methods: addition and concatenation. How does addition work?
Addition is pretty simple. You just sum the feature vectors of the text embeddings and the time series embeddings element by element. It's computationally cheap because the size of the resulting fused embedding doesn't increase. It kind of lets the text information modulate the time series representation. Studies like TimeMMD, GPT-4MTS, AutoTimes, and T3 have used addition for time series tasks. Mathematically, it's just PMPX plus ETA, straightforward enough, and concatenation.
Concatenation is also direct, but instead of adding, you just stick the two embedding vectors together end to end. So if eSex has dimension $D and $E has dimension D2, the concatenated embedding $E has dimension $D plus D2.
Ah, so it creates a longer vector.
Exactly.
Yeah.
E's parallel E key 2, where parallel is just concatenation. This potentially keeps more distinct information from both, but results in a higher dimensional space. Examples using concatenation include unitime, CGLM, tempo, and time FFM.
And it looks like some research even mixes these fusion techniques. Yes, absolutely. For instance, time LLM and S2I key LLM might use concatenation after doing some retrieval-based alignment first. FCSA uses concatenation for fine-grained feature extraction, and T3 actually uses both. It adds embeddings first, and then concatenates the result later in its process. It shows there's flexibility in combining these methods to try and get the best of both worlds.
Okay, we've covered the types of text and the main strategies, alignment and fusion for integrating them. Let's get to the results. What did the experiments actually show about how well these different approaches work?
Right, the empirical evidence. The survey summarizes experiments run on quite a few different data sets covering agriculture, climate, economy, energy, health. So a good range of domains. The textual data used was exactly what we discussed. Numerical prompts, PN, statistical prompts, PS, often expert reports, contextual prompts, PC, like news summaries, and those word token embeddings, W, from pre-trained models like GPT-2.
And the strategies tested.
The focus was mainly on the most common ones found in the literature. Unidirectional retrieval for alignment, and then concatenation and addition for fusion. The main task they looked at was time series forecasting that made up about 2/3 of the tasks reported in the papers they surveyed. Crucially, they always compared against a baseline model that only used the time series data, no text input. That's how you measure the benefit of adding the text.
Makes sense. You need that benchmark.
Exactly. Table 1 in the paper details the data sets things like frequency, monthly, weekly, number of samples, time spans, which could be quite long, like 1980 to 2024. And Figure 3A visually shows those 4 text types again.
So what were the big takeaways from these experiments? Did adding text generally help?
Yes, the overall picture was pretty clear. Adding textual data can significantly improve forecasting accuracy. For example, they mentioned a case in the climate domain where using retrieval-based alignment with numerical prompts cut the mean squared error, the MSE, by over 22% compared to the time series-only baseline. That's a substantial improvement.
Wow, okay.
And there was a general trend. Numerical prompts, PN, and statistical prompts, PS, usually gave the biggest performance boosts. Which kind of makes sense, right? That text is directly encoding the numbers or their key statistical properties, so it has a very direct link to what the model is trying to predict. Contextual prompts and word embeddings tended to be less impactful, though still sometimes helpful.
That aligns with intuition. What about comparing the prompt types themselves? Did one usually come out on top?
The experiments suggested that numerical prompts, PN, often perform the best across most domains, especially climate, energy, and health forecasting. They consistently led to bigger error reductions compared to, say, contextual prompts in those areas. Statistical prompts, PS, also showed strength, particularly for economic forecasting. You can imagine expert reports or economic indicators being very predictive there. Interestingly, the word token embeddings, W, just using the general pre-trained LLM embeddings, usually performed the worst in these forecasting tasks.
So just grabbing generic embeddings isn't enough.
It seems not, at least not without more specific integration. It suggests that while LLMs have powerful general language understanding, you need more tailored text representations or integration methods to really capture time series specifics effectively.
Okay, and how did the strategies alignment versus fusion stack up against each other?
The results generally favored alignment, specifically retrieval-based alignment. It often outperformed both addition and concatenation fusion methods, especially when paired with those effective numerical and statistical prompts. For example, in the economy domain, retrieval with numerical prompts reduced MSE more than just concatenating the numerical prompts. Addition often beat concatenation, but it generally lagged behind retrieval and didn't work well at all with the word token embeddings.
So retrieval seems like a strong contender.
Yes, it appears quite promising based on these findings. Figure 4 in the paper shows a typical experimental setup. A pre-trained LLM like GPT-2, often with frozen weights to save computation, a time series encoder, the alignment fusion layer, and then a task-specific head for forecasting.
Were there noticeable differences across the different application domains? Did certain methods work better for certain types of data?
Yes, definitely some domain specificity. Economy and health forecasting seem to get the biggest benefit from numerical and statistical prompts, perhaps because those fields often have structured reports or clear indicators that translate well. Climate and agriculture saw more moderate improvements. Maybe because they're affected by a wider range of factors, some harder to capture in text.
Plausible.
And interestingly, for energy forecasting in their tests, addition-based fusion with numerical prompts actually did better than other methods in that specific domain. So it really highlights that there's no single best approach for everything. You really need to consider the domain, the kind of time series, and the available text when choosing your strategy. Table 2 summarizes these domain-specific results quite nicely.
Right. It's definitely not one size fits all.
Mm.
The choice of text type and integration method seems highly context-dependent. Looking ahead now, what does the paper point to as key future research directions? Where is this field heading?
The paper lays out several important directions. A big one is moving towards multimodality modeling. So going beyond just time series and text to maybe include images, video, audio, other relevant data types. With the rise of powerful multimodal LLMs like Meta's Llama 3 that can handle images and text together, there's potential for much richer, more holistic analysis, especially in domains where that kind of data exists.
That feels like a very natural evolution, combining even more data sources. What else?
Another key area is just improving effectiveness. While these LLM methods show promise, they don't always beat simpler, specialized models. And overfitting is a real risk with these huge models on potentially smaller time series datasets. So future work could look at things like dynamic model selection, choosing the right approach for the specific data or meta-learning, or ways for models to continually adapt and improve over time.
And the elephant in the room with LLMs is always the computational cost, right?
Absolutely. Efficient optimization is critical. These models are demanding. Processing long time series with complex LLMs takes a lot of compute power. We need more research into lightweight architectures tailored for time series, more efficient attention mechanisms that scale better, maybe adaptive frameworks that adjust compute based on input complexity. The paper mentions things like last token storage or knowledge distillation as existing steps in this direction, but more innovation is needed.
And finally, the black box problem. Interpretability must be a concern here too.
Yes, transparency of LLMs is a major point. It's often hard to know why an LLM makes a certain prediction for a time series. What factors did it weigh most heavily? This lack of transparency is a barrier to trust, especially in high-stakes areas like finance or healthcare. Plus, LLMs can sometimes hallucinate or make things up, which is obviously bad for forecasting. So future research really needs to focus on making these cross-modal time series models more transparent and explainable.
This has been a really thorough deep dive. Okay, so to quickly recap, integrating text with time series using LLMs looks very promising for improving analysis. But how you represent the text, numerical, statistical, contextual, or embeddings, and how you integrate it, alignment like retrieval or fusion like addition concatenation, matters a lot. The best approach seems to vary by domain and data type. And the experiments suggest alignment, especially retrieval, often has an edge over fusion strategies.
That's a great summary. It's still early days, really, but the pace of research is fast. We're seeing rapid development in techniques to bridge this gap between text and time series. The findings give us good clues about what works best where.
And clearly, big challenges remain efficiency, interpretability, consistently beating simpler models. But the future directions, multimodality, better effectiveness, efficiency gains, more transparency, suggest this is a really active and potentially transformative area for analyzing temporal data using LLMs.
For sure. The combination of improving LLM capabilities and ever more diverse data sources points to some really exciting possibilities ahead for time series analytics.
On that note, here's a final thought for you, our listener, to ponder. As these LLMs get even smarter and we gather more kinds of data text, images, maybe even sensor data, how might integrating all this nuanced information truly revolutionize our ability not just to predict, say, economic shifts or climate changes, but to actually understand the deep, complex causal forces driving these systems? That's a question that will surely keep researchers busy for years to come. Thank you for joining us for this deep dive.